Today we're going to talk about more probability, so you need the information from the yellow sheet, basic probability, favorable outcomes over total outcomes, and we're going to apply it to what if we're doing more than one thing. Did you not get a sheet?
Yeah.
Okay, I want to pass one back to you. So first thing we want to do is talk about the definitions for independent and dependent, and before I go to the next slide, let me just ask you, what does the word independent mean to you outside of math? It doesn't depend on something else to work? You're free? Anything else? What's that? It might cause something to happen. I like those. And then what does it mean to be dependent outside of math? You rely on someone?
Maybe like an outcome.
Oh, it is the outcome?
Yeah.
Okay, so, I get it. So, like, independent makes something happen, and then dependent is what does happen. Okay. Yeah. Other words for dependent? I like both of those definitions that you're using, and what I want you to think about is how those can be related to what we're going to talk about today in terms of probability of different events. So for independent, you said you're free. You don't depend on anything else. So maybe we could say, like, without using the word depend, you're on your own. And so independent events in math means the result of one event does not affect the probability of the events that follows. It does its own thing. Two key words that show up, or at least some idea of these two words show up, and that's the words with replacement. So like if we're talking about drawing things, like let's say that example I used last Friday where I put your names into a hat and then I was going to draw names. If I'm going to give a prize, a piece of candy to all the names that I draw, and I draw 3 names, they would be independent events as long as I put your name back in the hat. Okay, which some people might argue is not fair if Kylie has the opportunity to win 2 pieces of candy, but it would make it independent events where I put her name back in the hat, so I still have 21 names to choose from. Okay, so the probabilities don't change. Dependent events, I think you could probably figure out, is just the opposite of that. And I like Kyle's definition. They're events, or like when you're dependent, you rely on someone else. So if we're talking about a dependent event in math, our probability relies on what happened before us. So the probability of one event does affect or change the probability of the events that follow. Also, on the opposite side of that spectrum, instead of seeing the words with replacement, we'd use the words without replacement. So that if I'm talking about that example where I'm putting your names into a hat, this time I'm going to pull 3 names, give all the winners a piece of candy, and I'm going to, if I pull Sahil's name, I'm going to keep that name out of the hat. So now your probability for the second draw is dependent on the fact that I pulled Sahil's name. There's one less name in the hat, so you have a better probability of getting your name pulled on the next draw. Okay? And that would be true if I drew another name. So what's really happening with independent and dependent events is we're talking about something, you could call them consecutive events, events that happen one right after another. Okay, so we're also going to hear the words and then. Hang on just 1 second. Is this Ms. Conkey? Yes? Yes. Can you go to Mr. Brown? I have a feeling she knew that was coming. Okay. So on the next part of your notes, you've got 3 examples that I want you to either define as independent or dependent. I'm going to give you 1 minute to read them silently to yourselves and make your own decision. And then after that minute's up, I'm going to have you talk about it with your shoulder buddy. But make sure you have an answer for each of those. Okay. Let's come together and talk about the examples there on your worksheet. Riley, what did you say for the first one? And why? Okay, yeah, you're replacing the card. You're putting it back in, so it's the same as when you started. Okay. What about the second one, Jace? Dependent on your reasoning? You kept the card, and that changes probabilities that happen after it, right? There's one less card in the deck. And if you pulled a king, there's one less face card in the deck. Okay, so that changes that second probability in a couple of different ways. A month is selected at random. A day of the month is selected. Can I do first a raise of hands? How many people think independent? And how many people think dependent? And how many people just don't know? Okay. Okay, so let's make some arguments. For independent, what's your argument for independent?
Actually, couldn't it be both? Because the month is independent, and then since the day of the month is selected, that part is
Okay, so I see what you're saying. You're kind of splitting up into different probabilities. I think the key to independent and dependent is that, like, the first event will always be sort of on its own, right? It's like you'll always have an independent event first. Like the second example, you draw a king. That would be 4 out of 52. It's independent. You haven't drawn any cards. It's fine. So when we're classifying independent and dependent events, we really want to think about the 2 events together. Okay. So if that second one is not changed by the first one, it would remain independent. If the second probability is changed by the first one, then you automatically classify those 2 events as dependent. Okay, so if I kind of clarify that and say we're naming 2 events in relation to each other, would you keep your answer of independent? No, you would change it to dependent. Anybody else think independent originally? That wants to share their argument? Okay, so then I'm going to kind of move aside. Who said dependent and has an argument for that? Jackson?
Dependent because some months have less than 31 days. So if you got October 31st for October because you chose October for the month, but some months like November, right? 30 days. So if you got November, then the reason you can't get 31, the reason you can't get 31 is because you chose
Oh. How about February? Can you pick any day you want in February? Up to a certain amount, right? But February has less days than all the other months. So I would argue that the third one is dependent. Okay? And hopefully if you were kind of questioning that one, if you had maybe thought independent, hopefully Jackson, I thought you did a really nice job of explaining that, giving an example. In October, I can pick 31. In November, I can only go up to 30. Okay, so it really depends on what month you pick, what the number of days are. Now, some people may argue, but I could pick 10 in either month. That's true, but there is a limit depending on which month you choose. So we would call those dependent events. Okay, next up we want to write down the formulas for independent and dependent. These are not difficult formulas. They're actually very easy. So the first one is the probability of A and B is equal to the probability of A times the probability of B. Notice that underneath the word and, I put a little extra then, because I want you to be thinking about these events, like I said earlier, they're like consecutive events. So we're doing more than one thing. We're drawing a card and then another card. And then we can compare those 2 events separately. Later, we'll see next week another probability of A and B, where and means at the same time. So you're going to eventually have to kind of deal with two different ands in probability, and they mean different things. Okay, so a lot of times I put the and then there to kind of remind myself that I'm talking about two different events. Now, there's a formula for dependent events, and I want you to write it down, but I will say this as you're writing it. It's the same thing. The probability of A and B is equal to the probability of A times the probability of B with a little extra condition. And there's that line with the A after it. Okay. We say this piece right here as the probability of B given A has already occurred. Probability of B given A has already occurred, and that's that extra condition. This only happens with dependent events because that second probability depends on what happened in A. And we have a name for that. We're going to talk more about it on the back side of our notes here at the end of class, but it's called conditional probability. Okay, so you'll see that again, conditional probability. And it just means it's probability with condition. So it's like when you don't replace something. What about that example where we're drawing a king and then a face card? If we don't put the card back, then our probability of a face card won't be 12 out of 52. It will change and it will be 11 out of 51, and we have to consider that. You can also have like conditional probabilities where maybe like you can't count it, so it's not like pulling a card or pulling a marble. And a good example that I think to share with you guys is like maybe you get invited to go with a group of friends to the movies on Friday night. And you might be like, yeah, it's like 50-50 if I'm going to go. But then maybe you find out someone else is going. And that might change your probabilities. Then you'd have like a dependent probability. Well, it's probably 50-50 if I go, but if Sierra goes, I may be more or less likely to go depending on I like or dislike Sierra, right? But could you relate to that? That like you make certain decisions and then on some of your probabilities it would be dependent on if someone else is going to be there, a friend or an enemy, I suppose. Not that you would have any enemies. Okay, but think about that. That's a conditional probability. Okay, let's do a couple examples. A bag contains 21 $1 bills and 5 $100 bills. You randomly draw a bill from the bag, you set it aside, and you randomly draw another bill from the bag. Find the probability that the first and the second bill is a $100 bill. I'm going to give you just a minute or so to kind of play around with that. Figure some probabilities. What are some things that you're going to need to know? And then we'll come back and we'll talk about it. But read through it again if you need to. Sort out some numbers. I'm going to use my probability notation. Instead of A and B, I'm going to say the probability of a $100 bill and another $100 bill, where that implies and then. What are some things as you're kind of rereading it and looking it over you thought were going to be helpful to calculating the probabilities? What do you need to know? Total number of bills. So your total number of outcomes, which is 25, right? Okay, so we've got $21 bills, we've got 5 100s, so we have 25 total. And that helps you do basic probability for the first $100 bill. What's the probability of pulling a $100 bill on your first try? What's that, Sahil? 5 out of 25. Okay, not hard to do. That's basic probability from Monday. You have 5 favorable chances because there are 5 $100 bills in the bag. You have 25 total outcomes. So 5 out of 25. Okay. I'm going to go ahead and label that the probability of 100. Now, we want to know what's the probability of drawing 100 and then another 100. And what we need to think about in this particular section is, are those independent or dependent events? Based on what you read in that scenario, is this independent or dependent? Dependent. What gives it away as a dependent event? You're setting it aside. So this would mean without replacement. Which means for our second probability, we have to consider that we pulled a $100 bill on the first one and we put it off to the side. What will be our new probability for a $100 bill? 4 out of 24. There's one less $100 bill in the bag because you set it aside, and there's one less total bill in the bag because you set it aside. So 4 out of 24. And this I could label as the probability of 100 given I already grabbed 100. Okay, so that's a conditional probability. If it was an independent event, it would have just been 5 out of 25 times 5 out of 25. Now, one thing I want to share with you is, on these problems, when you have some fractions that have like either larger numerators or denominators, rather than mess around with fractions, because with larger numbers I'm going to have to work to simplify it and stuff like that, I'm just going to put it into my calculator and get a decimal. So I want you to practice putting it into your calculators real quick. Make sure you're okay with multiplying fractions. Just 5 over 25 times 4 over 25. Okay, and over would be divide. So 5 divided by 25 times 4 divided by 24. See if you can get the correct answer. So I like to, for a lot of these problems, just in probability, write my answer in decimal form. 0.033. You could change that to a percent if you wanted to. That's about 3.3%. Do you have a very good chance of pulling 2 $100 bills? Not really. But I think people will fare better by not using fractions here, because then you won't lose like half a point for not reducing your fraction. Is everybody okay with this? Okay, I'm going to give you another minute to kind of read through and set up number 2 example. So can you read through number 2 and work to set that up? As you're reading that question, what are some things that we might be wondering about the deck of cards? Anybody have any questions about the deck? How many of the cards are hearts? 13. How many of the cards are red? 26. Help you answer some of your probabilities. based on what I read in example number 2, part A and part B are asking for two different types of answers. One where the events are independent, I replace the card, and one where the events are dependent, I don't replace the card. So we kind of shared out some things. The number of hearts is 13, the number of red cards is 26. For part A, if we want to pull the probability of a heart and a red card, what's the probability of pulling a heart? A heart? 13 out of 52, and we're going to multiply it by the probability of pulling a red card, which is 26 out of 52. Or you could write 1/4 times 1/2. Okay, this is the probability of a heart. This is the probability of a red card. And we should come up with like 0.125. Now, we have the same problem in part B, but now we know we're working with something that is dependent. So our first probability won't change. It will still be 13 out of 52 for pulling a heart. But now we need to work with the second probability, which is what's the probability we pull a red card given that we've already pulled a heart? Okay, so how many cards were red? 26. Is a heart a red card?
Yes.
Yes, so there's one less red card, so it should be 25. We used to have 52 cards, now we have 51 cards. And then you can just multiply those fractions. I think that one comes out to 0.123. Question?
So you only want one red card or a heart card?
You pull two cards.
Okay.
The first one is a heart, the second one is a red. Okay. Any questions other than that I can answer in that problem? What I really need you to think about is this is finding basic probabilities and multiplying them together. The only sort of tweak there is if you have to change the second probability because you didn't put the card back or the marble or the name or whatever it is. Okay, on the back side, we need to talk about conditional probabilities. So I'm going to have you jot these things down. We'll try to get an example done before you leave. We've already said a little bit about conditional probability, and this really says the same thing I said about conditional probability on the last slide. It's defined as the probability event B occurs given event A has already happened. You only have conditional probabilities with dependent events. Think back to how we use the word dependent in the English language. Kyle said to rely on something. So when an event is dependent, it has a conditional probability, a probability based on condition. Independent events don't rely on each other. They don't have those conditions. They have their own separate probabilities and nothing messes with it. With the same notation you saw in the formula for dependent events, the probability of B given A. Okay. There's nothing mathematical to do right here. It's just a way to name it as something that's dependent, like you saw in the last example when I did a heart given, a red card given a heart. Okay. It just means that's a dependent probability. Now, the formula that you're writing down is the same formula that you saw on the front side of your notes. For dependent events. But what we did was we said, how can you find the conditional probability of B given A? If it's being multiplied by the probability of A, then I should divide by the probability of A. So that's where this formula is coming from. It's the same formula as before, it's just saying if we knew the conditional probability or we wanted to find the conditional probability, let's divide. Let's look at an example. Okay. So we're going to study more with tables tomorrow, but this is kind of a good introduction so that you can just see two tables. A computer lab has 10 computers. Some have CDs, some have DVDs. Some are new, some are used. Okay. A student picks a computer at random. Use the table to find the probability. What's the probability they pick a new computer? How many are new? 7 new ones. 4 with CDs and 3 with DVDs. So 7 out of 10. What's the probability they pick one with a CD drive? We're looking at the total CDs, which is 6 out of 10. What's the probability they pick one that's new and has a CD drive? How many are new and have CD drives? Only 4. Okay, so that would be 4 out of 10. Now here's where we get to conditional probability. What's the probability it's new given that it has a CD drive? How many computers have a CD drive? 6. So that's our total that we can choose from. Okay, we're given that it has a CD drive, so we're choosing from those 6. What's the probability within that 6 that it's new? 4. So there's an example of a conditional probability where, based on the condition, we're not going out of 10 computers anymore. We're going out of those 6 that have CD drives. And we could certainly reduce these. Now, your homework assignment is at the bottom of the green notes. Okay, so at the bottom of the yellow notes is your homework assignment for Monday. Bottom of the green notes is your homework assignment for tomorrow. Please